spills: natural cleanup, containment and recovery, chemical dispersion, and shoreline cleanup. In many cases, a combination of all four will be required. This introductory program looks at the oil spill. An accident such as this can have disastrous consequences: miles of fouled shoreline, damage to wildlife, and the disruption of whole communities. Tanker accidents and offshore blowouts have increased public awareness of oil spills and are often seen as the major source of pollution of our seas. But in reality, these large and sensational events account for a little over 10% of the petroleum hydrocarbons introduced into the ocean. Municipal and industrial wastes, natural seeps, and routine marine transportation losses all contribute to a total input of around 3.5 million metric tons a year. Considering our world's current demand of 3 billion metric tons per year, the amount spilled can seem relatively small. But accidents happen, and this is of little consolation to the coastal communities affected by an oil spill. Clearly, prevention of spills is a high priority. In recent years, governments and industry have focused attention on the improvement of operational procedures and the design of equipment, and much has been done to reduce these losses. Despite improvements in navigational safety and training standards, the scope for reducing the incidence of accidental oil spills remains limited. Human error will always be the major underlying factor in the cause of such spills. Well-trained personnel can minimize the impact. Oil spill control is never easy, but knowledge of the behavior of oil, equipment, and organization can make the task easier.
Analysis of tanker spills occurring throughout the world showed that the majority are small and take place in port during bunkering and routine cargo handling operations. Major spills are less frequent and tend to occur in ports, port approaches, and areas of high traffic density as a result of collisions and groundings. But world statistics seem less important when acute accidents release large volumes of oil into a small area at a high rate. When this occurs, it's important to know how to cope.
Crude oils and products are complex mixtures of hydrocarbons which have a wide range of physical and chemical properties depending on their composition. Light crudes and products, such as petrol and diesel, although toxic to marine life, quickly evaporate and dissipate, whilst heavy crudes and viscous fuel oils are less toxic but are resistant to both natural breakdown and cleanup. Understanding the composition of oils can help with the decisions on cleanup techniques. As soon as oil is released into the sea, it undergoes a series of changes termed weathering. Some help and some hinder an oil spill response team. It spreads and drifts, making location and containment difficult. But it also evaporates, disperses, and eventually degrades naturally. If no sensitive resources are threatened, monitoring the movement and fate of oil slicks through aerial reconnaissance may be all that is required. Unfortunately, rates of natural dissipation are slow, and all too often, the oil will reach the coastline. When oil first enters the water, it begins to spread. This spreading is the result of wind and currents, as well as gravity and the difference in the surface tension between oil and water.
Initially, gravity will act on the oil and it will become thinner and cover a greater area. In the early stages, the oil will spread more quickly, especially if there are large quantities. Further spreading depends more on surface tension effects and viscosity, and so is less affected by the thickness of the oil. The further fate of oil can follow this path: drifting, evaporation, dispersion, emulsification, biodegradation, and sedimentation. These processes vary in importance according to the conditions and type of oil. For instance, light products will evaporate completely within hours, but heavy fuel oils will lose very little volume through this process. Spills of such heavy oils frequently result in widespread contamination of shorelines and cause the greatest problems to cleanup teams. Another problem is emulsification. This is the process where up to 80% of seawater is absorbed by the oil to form a mousse. This greatly increases the amount of pollutant.
Local knowledge of wind and currents will assist in tracking spilled oil. It has been observed that floating oil will move downwind at about 3% of the wind speed. The oil will also be affected by the surface currents in the sea, and without wind, a slick will move at the same speed and direction as the surface current. Simple geometric calculations that take account of wind, current, and elapsed time will enable a search area to be identified.
Here, the last known position of the oil has been marked on the map. The current of 0.5 knots in its direction is plotted. The speed of the current is represented by the length of the arrow. The wind direction is also plotted, the length of the arrow being calculated as 3% of the 25-knot wind speed, that is 0.75 knots. The direction and speed of the oil is estimated by drawing a vector diagram. In this case, the resultant is 0.9 of a knot in a southwesterly direction. Computer models are also available for the purpose of predicting movement. In reality, there are often many difficulties in precise calculations. Inshore currents or local wind conditions may not be known, or can change and disrupt the pattern of oil movement. Because of this, a systematic ladder search may be the most effective method of surveying an area.
The aircraft chosen for aerial observation should feature good all-round visibility and carry suitable navigation aids. The distance of the spill from shore and the area affected will determine whether single or twin-engined helicopters or fixed-wing aircraft should be used. Weather conditions, flight duration, and fuel availability may restrict the operations. It is essential to talk through a proposed flight plan with the pilot on the ground to avoid misunderstanding in the air. Here, the pilot's advice is to select the flight direction so as to lessen the haze and dazzle from the sea. Polarized sunglasses are also an aid in these circumstances. Occasionally, more sophisticated aids are used. Radar devices can detect oil spill location, and other sensors can give an indication of slick thickness. Where such devices are not available, it's advisable to verify initial sightings by overflying the area at low altitude. Seaweed, underwater formations, cloud shadows, and sewage discharges can all be misleading phenomena. This sighting is assessed to be a deliberate discharge, as its small area, symmetry, and location distinguish it from an accidental oil spill. Later, the crew locates several windrows of oil. A low-altitude pass confirms their sighting, and they're requested to quantify the oil. An accurate assessment is virtually impossible, as it's difficult to gauge the thickness and percentage coverage. Here, an on-the-spot calculation is made by flying at a constant logged speed over the mousse and silver sheen. Use is made of specialized navigational equipment to plot positions. The passes are timed and noted, and aerial photographs taken for further assessment. Direct radio communications with the control post on the ground allows the appropriate response measures to be put rapidly into effect.
Assessment of the type and thickness of oil can have a considerable bearing on the estimated volume of the slick. In this case, the ratio of mousse to sheen was estimated to be 1 to 9. Observations from the aircraft indicate that the total area of oil is about 14 square kilometers. Typical mousses are about 1 millimeter thick and are made up of half water, half oil. In this case, the mousse constitutes a tenth of the total oil surface and could contain up to 700 cubic meters of oil. The sheen, on the other hand, although covering 9/10 of the surface, is about 1/1000 of a millimeter thick and only contains 1.5 cubic meters. These calculations show how crucial it is for the observers to distinguish between mousse and sheen.
As the oil approaches the shoreline, a knowledge of the location where floating debris collects is useful in predicting where oil may accumulate naturally. Small coves, inlets, and areas under jetties and piers are all examples of collection points. The appearance, persistence, and impact of stranded oil often depends on the type of shore that it reaches. Shorelines vary. Exposed rocky shores, pebble beaches, sandy beaches, and sheltered marshland, all with different appearances and different characteristics. Mangroves, for instance, act like a sponge. The oil becomes trapped and difficult to remove. Others contain nooks and crannies holding the oil in pockets. But oil rarely persists on rocky shores in angry seas. Maps and charts showing shoreline types, together with case histories of previous pollution incidents, can provide invaluable information at the time of a major spill. To a certain extent, the behavior of the spill can be anticipated and the appropriate countermeasures taken. Before an incident is confirmed and major action taken, it is advisable to inspect the shoreline at close quarters. Smell, texture, and color are important to note. This sample was found to be vegetable oil, and this sighting turned out to be seaweed. Black mineral grains and dark stones can also be misleading. When an oil sighting is confirmed, immediate and thorough recording of information can save time and money later. Photographic records of the appearance of oil on shorelines are useful not only to support the descriptions of the location and appearance of oil, but to serve as a record for later changes in the extent of the pollution. The knowledge of the oil weathering process and local winds and currents may help detect its source. The chemical analysis of carefully collected samples to confirm this may be vital for subsequent compensation claims. Clean glass jars or metal cans avoid contamination during storage, and careful labeling showing time, date, location, the collector, and witness will prevent later confusion.
Sampling can assist with identification, but for the purpose of arranging shore cleanup, it is important also to estimate the amount of oil on a stretch of beach. Assessment is largely visual and often difficult. For instance, sand, vegetation, or ice can all obscure the pollution. Where visible, the oil can be quantified by helicopter and shoreline surveys. Rough calculations of volume can be made by measuring the thickness of small representative areas and by multiplying the average thickness by the estimated total area covered.
Unfortunately, this method often results in large errors, as oil can penetrate the beach to varying degrees. Precise calculations are practically impossible. Stones and crevices, seaweed and other debris, and mousses can often influence the calculations to give misleading results. In many cases, descriptions of light, moderate, or heavy contamination are a useful shortcut to describing the degree of oil pollution. Photographs from previous incidents can provide the basis of uniform descriptions of the level of pollution from different observers. The quantity of oil may not always reflect the severity of an oil spill incident. A little oil in a sensitive fishing area can cause more harm than several tons of oil on a desolate rocky coast. The effects of a marine oil spill can also mean different things to different communities. A stretch of soft sand covered in oil may be a mere nuisance to some, or a catastrophe to others. Each community will assess its own priorities: recreation, industry, fishing, mariculture, marine life, sensitive habitats. All these resources can be adversely affected by oil, but it will be impossible to protect them all to the same extent in a major spill. Often, public opinion and pressure can force cleanup in areas where the natural elements would fare better. Despite this, conflicts of interest may still occur. People whose livelihoods depend on tourism may demand rapid restoration that may be ineffectual and damaging. Certain techniques may also create longer-term problems. For example, removal of oil from marsh vegetation may result in long-term damage. The leader of an oil spill response team needs to be aware of these problems before an event. He will need a thorough knowledge of the effects of oil under different conditions in different areas, and the diplomacy and skill to communicate them to communities under threat.
Can you make sure you know the procedure?
Oil spills are rare, but when they do occur, they can be disastrous in the short term, ecologically and economically. Many people, authorities, management, and operators have become wise after the event. It is easy to put off time-consuming preparation for an unlikely event, but this has often been regretted. Investment in training will pay off in an oil spill. The management skills, coordination, and planning will also be of benefit in their everyday work. To help prepare for the event of an oil spill, this film has looked at the importance of understanding the fate of oil from spill site to coast, some of the methods of detecting and locating oil spills, and ways of assessing the contamination.
Dry ground.
If a spill does occur, important decisions will have to be made, not least the options of leaving the oil to dissipate naturally or cleaning it up. The next 4 films will look at containment and recovery, the use of dispersants, shoreline cleanup, and planning and operations.
Thank you.
Preparation for an oil spill can never be too thorough. Training, planning, and practical exercises may help prevent this, and this, and this. Oil spills may be rare, but accidents like this have happened and will occur again.